so that magnitude of vector remains unchanged under rotation. We know magnitude of a vector is a scalar quantity, so it must be invariant, or the magnitude of vector must not be changed under rotation. Consider a vector. Suppose a vector is equal to I cap ax plus j cap ay. I cap is the unit vector along the component ax, j cap is the unit vector along component ay. Suppose this is ay, not az, ay. And if you find out the magnitude of the vector a, then this will be equal to x square plus ay square root. Now we'll see after rotation whether the magnitude of the vector a will change or not. Suppose the vector a rotates about the z axis about an angle theta. The vector a rotates an angle theta about z axis, and after rotation the component of the vector along x axis, suppose x prime, that is equal to x cos theta plus ay sin theta, and the component of the vector along y, that is ay prime, after rotation, that is equal to minus x sin theta plus ay cos theta. And this thing we have discussed in the video. You watch the previous video so that the components of vector may change under rotation. That means if a vector will rotate, then the component of the vector will change like this. I have explained it in the video. Components of vector may change under rotation. Now we'll find out what will be the magnitude of the vector. Magnitude of the vector a prime, that will be equal to x prime square plus ay prime square. X prime square is equal to x and its square root. X prime is equal to x cos theta plus ay sin theta. So x prime square will be equal to the whole square of x cos theta plus ay sin theta whole square. Similarly, for the y component, for the y prime component, that will be equal to minus x sin theta plus ay cos theta whole square. So this will be simple a plus b whole square. So x square cos square theta plus ay square sin square theta plus 2x cos theta into ay sin theta. Similarly, from this it will be equal to x square sin square theta and plus ay square cos square theta minus 2x sin theta into ay cos theta, and 2x cos theta ay sin theta, here also minus 2x cos sin theta into ay cos theta, this will cancel. And if you take common from this term and from this, if you take common x square, then in the bracket you have sin square theta plus cos square theta, which is equal to 1. Similarly, from these two terms, if you take ay square common, in the bracket you have sin square theta plus cos square theta, which is equal to 1. So the result will be x square plus ay square square root. So you see the magnitude of the prime component of the vector or the prime vector after rotation, that will be same as the magnitude of the vector before rotation. Before rotation, the vector magnitude of the vector is equal to x square plus ay square, what we have written in equation 1, and after rotation, an angle theta, the magnitude of the vector, that means the vector will change, because the magnitude will not change but its direction will change. That is why the vector will change. So you write the vector as a prime. That is why the magnitude of the vector a prime, that is equal to x square plus ay square square root. So in this way you can prove that magnitude of the vector remains unchanged under rotation. And the simple physics is magnitude of vector is a scalar quantity, so it must be invariant or it must not be changed under rotation.